Okay, in this exercise, we're going to derive the Michaelis-Menten equation. So basically, we start with an enzyme plus a substrate, and then we get an enzyme substrate complex, which is an intermediate molecule, but the final product is going to be the enzyme again, which dissociates. So an enzyme can be reutilized over and over. So at the end, we get the enzyme again plus some kind of product. So this reaction is going to happen forward and backwards, and then the rate constant is going to be K1 for the forward reaction and K minus 1 for the backward reaction. And then this reaction over here from ES to enzyme product also has a rate constant. It's going to be K2, and it also has a K minus 2 constant for the backward reaction. However, this analysis is done when the time is 0. So when the time is 0, we only have enzyme plus substrate, and we don't have much product at that time. So the backward reaction is basically not happening, or is basically negligible. So we're not going to be using the K minus 2 in our calculations because it's negligible. So this will not be in the calculation. So we need a starting point. So if you look at the graph of the velocity of the reaction velocity, we're gonna have a substrate in the x-axis and the velocity on the y-axis. And then the curve is gonna be something like this. Then this is gonna be our Bmax. So in the end, we need a Michaelis-Menten equation is going to be in terms of the velocity and the substrate concentration. So we need an equation for that. So we start right here. So velocity is going to be K2 times the enzyme substrate complex. So this will be our equation 1, which from here we're gonna proceed to derive the rest of the equation. So at this point in time, from at the beginning, we're gonna have a rate of formation of enzyme substrate complex. So the rate of formation is gonna be equal to, so the rate of formation of ES is going to be equal to, so we're going this way, basically we're going this way, but it's K1, right? So we're using K1 times the concentration of enzyme times the concentration of substrate. And then there's also a rate of dissociation. So the rate of dissociation going to be equal, and the rate of dissociation is going to go two ways. So it's going to go this way, it's going to dissociate into enzyme product. It's going to go this way, it's going to dissociate into substrate and enzyme. So we're going to have, if we come this way, so we're going to have K minus 1 times ES plus the other way is going to be K2 times ES. Now, at this point, we need to make an assumption, and that assumption is the steady state condition. And what it is that it states that the rate of formation and the rate of dissociation are equal. So I mean that these two equations are equal. So from that assumption, we can get the rate of formation, which is K1 times ES, equals the rate of dissociation, which from here already I can factor this, and then it's going to be K minus 1 plus K2 times ES. So solving this and putting all the like terms on one side, we get ES over equals to K minus 1 plus K2 over K1. And what Michaelis-Menten did was, so he defined this term K minus 1 plus K2 over K1. He gave it another name, and this is a new constant. It's the Michaelis constant. So this right here is the Michaelis constant. So we can rearrange this, all this, into enzyme substrate complex equal to enzyme concentration times substrate concentration divided by Km. We can, this would be, so we got this equation right there. Now, at the beginning of the reaction, so basically when the time is 0, right? So we have the total substrate concentration is equal to the substrate concentration plus the enzyme substrate complex. And what happens here is that at the beginning of the reaction, we're going to have enzyme and substrate and enzyme substrate complex, but the substrate concentration is going to be much larger than the enzyme substrate complex, because usually there's a lot of product and very little enzyme. So this amount is going to be almost negligible, almost 0. So the total substrate concentration is going to be almost equal to the substrate concentration. And so this term right here stays the same. We can leave this term the same. Now we do the same for the enzyme concentration. So enzyme concentration total is going to be the enzyme concentration plus the enzyme substrate complex, but we cannot make anything 0 here because it doesn't work. At the beginning the amounts are little and we don't know how much concentration of each ones we have, so we just leave this like this, and we use this equation just to rearrange it and solve for ES. So, or basically solve for E. So we're going to replace this E right here. So now we get that the enzyme concentration is equal to the enzyme total minus the enzyme substrate complex. And then we use this equation here and replace it over here. So we get enzyme substrate complex is equal to E, which is E total minus ES times the substrate concentration divided by Km. So once we solve this equation, we get to enzyme substrate complex is equal to enzyme concentration total times substrate concentration times Km plus S. So now we have ES in terms of almost all substrate, and we have this, which is a constant, and we still have the E total right there. So we can go back to our first equation, which was and then replace this ES with this term right here. So that's gonna give us so it's gonna give us this equation right here. And now from here, what we're gonna do is we're gonna use the Bmax. So to try to get rid of this term right here. So the Bmax, we're gonna get a Bmax, which is gonna be K2 times when the enzyme substrate complex is at its max. And the maximum velocity is gonna happen when all the enzyme is bound by substrate. So there is no free enzymes. So there is no free enzymes. So basically what that means is that the enzyme substrate complex is gonna be equal to the E total. So we're gonna have Bmax is gonna be equal to K2 times E total. From here, we can solve for E total, and then what we're gonna get, E total is gonna be equal to Bmax over K2. So now, once we have this term, we can replace E total with Bmax over K2 over in this equation. So we're gonna have K2 and E total is gonna be equal to Bmax over K2 times substrate divided by Km plus substrate. So K2 and K2 eliminate, and then we get our final equation, which is going to be Bmax times substrate divided by Km plus S. And this is the Michaelis-Menten equation. That's it.